Hello, my name's Jeff Cumpston. I'm a postdoctoral researcher in concentrating solar power research. I work at the RWTH University in Aachen, which is in Germany. If I don't sound German, it's because I'm not. I come from Australia, and I've been there since 2016. And I'm here to talk to you today about the solar resource. So this is, I would say, the concept here sort of underpins most of the challenges that we face when dealing with concentrating solar power, because the fact that the solar resource is inconsistent and must be simulated and discussed in the first place is exactly why we run into trouble. So what, in terms of intermittent power generation, the necessity of storage and so on. So it's a very important topic, and how to model the solar resource is also very important, and how we can then use our understanding of the solar resource and our ability to model it in order to run simulations and to engineer power plants that run better is important. So this is the basis of the talk, and here's the outline. So first I'll just talk a bit more about the general the celestial bodies that we're dealing with here. We've got the Earth and the Sun, basically, and their location with respect to one another and how that affects the position of the Sun in the sky and so on. Then I'll talk about the propagation of the Sun through the atmosphere, which is something that does affect quite substantially the solar resource that we intercept at the ground level. And then the apparent motion of the Sun from the Earth's surface is very important. So particularly with technologies, with CSP technologies, because it is necessary that we track the Sun due to the fact that we're exploiting direct irradiance, which I'll speak about in the presentation. And then the next part of the presentation, we'll talk about the annual solar resource. And this is a short section, and it's basically, the annual solar resource is basically a good yardstick for how attractive a certain location is in terms of building a CSP plant. And then how we measure that is also something of interest. And we'll talk about data files that we can use to represent certain locations and the solar resource at certain locations in order to run our simulations and to do the engineering that we're all interested in. So first, here we have the Sun. This is the source of almost all of the energy that gives rise to life on Earth. And it's a hot sphere of hydrogen, basically. And the surface temperature is about 6,000 Kelvin, or more precisely about 5,780 Kelvin on average. So that changes depending on solar activity and other things. And its spectrum, and the radiation that it emits, closely resembles a black body. So this becomes important when we try to consider how to model the spectrum of the Sun in our engineering efforts. So here we have we have the Stefan Boltzmann equation with this sort of engineering style notation with small q representing heat transfer per unit area. So it's a heat flux, and it's a heat transfer rate. So here we have the Stefan Boltzmann constant here, and the amount of radiative heat transfer per unit area coming off the surface of the Sun, for example, is dependent on the fourth power of the temperature. So it's highly nonlinear. From an engineering perspective, this can sometimes frustrate our efforts in terms of simulation and optimization, because having a nonlinear term can complicate things quite a lot. And this is determined by integrating over the wavelength of the Planck's radiation law. And this is a relation which basically describes the curve or the spectral curve of the radiation coming from the sun, if we assume that the sun is a black body. And we can see it's heavily dependent on the wavelength. And it looks something like that. Okay, so it's a function of wavelength. We have the sunlight intensity in terms of kilowatts per meter squared per micrometer of wavelength. So that's the approximate solar spectrum based on the black body approximation. So this is just to move towards working out just how much radiation we receive at the surface of the Earth. If we assume that the radiation per unit area leaving the surface of the sun is follows our black body relation, then we can integrate over the whole surface of the sun and find out how much energy is leaving the sun in total. And that's simply multiplying by the area of the sphere of the surface of the sun. So that will become important in a second. I think this is a bit out of turn, so I might just leave that slide for later. And just talk about, so here we have, if we know the total amount of radiation coming off the sun, then we can say that the distance, over the distance from the sun to the Earth, we have a new sphere, which has a new area, and we can find the ratio of the area of this sphere to the ratio of the area of the surface of the sun, and this will give us our ratio of solar flux at the incident on the Earth above the atmosphere. So, and this ends up being about 1367 watts per meter squared. And that is known as the solar constant. It's not constant exactly, but it's to a good approximation. If you use that to characterize the flux density above the atmosphere, you'll be pretty accurate. So this is just what I was saying before. We've got the flux from the surface of the sun is spread over a larger area once it reaches the Earth's surface, and it's correspondingly the flux is lower. So there's nothing I haven't said there. It's just a different way of looking at it. So the solar radiation outside the Earth's atmosphere, it doesn't follow exactly that black body distribution. It has its own characteristics, which are based on the physics of the sun. But you can see that it does follow it fairly. What would you say? It has the same characteristics. It has a peak pretty much in the green, and it's pretty close to your ideal black body from that. The variation of the extraterrestrial radiation, here we have the solar constant, and it does vary throughout the year. Okay, and that's because the sun follows an elliptical orbit, and sometimes it's closer to the Earth. Sorry, that's because the Earth follows an elliptical orbit around the sun, and so sometimes it's closer to the sun than others. But we don't usually worry about this. We usually just consider the solar constant. All right. So that's just what I was saying before. Due to the eccentricity of the Earth's orbit, sometimes it's further away than others. January 2nd, the Earth is closest to the sun, and the 3rd of July, the Earth is furthest away. And the intensity varies about plus or minus 3%, which is exactly what we saw on the previous slide. Here we have another variation in the intensity of in the intensity of radiation leaving the sun, and this is an order of magnitude less than the variation due to the elliptical orbit. It's plus or minus about 1%, and this is because of the a natural cycle in the sun where sunspot intensity varies in 11-year periods. And here you can see it's varying. Here the solar constant is said to be about 1366, and there's a very small variation. And when the activity is higher, the peaks and the troughs are smaller, but nonetheless, it's not. I would say it's not really significant, but it's just good to know about that, and to know what magnitude it does have, particularly if anyone raises that idea, because this is a well-known idea that the sun has varying levels of activity, and it's good to know that just what that magnitude is in terms of the amount of radiation incident on the Earth. And I would actually say also in terms of, that's also important to know, because often sunspot activity is cited as a potential alternative theory for climate change by those who doubt the theory. So it's good to know that it's not actually that much of a deviation from the norm when you have high sunspot activity. So yeah, so the main point is the variations are typically small for solar applications in the radiation outside the Earth's atmosphere. So we do consider it to be constant. And there we've got the solar constant as 1366 watts per meter squared. And I suppose it depends on the source, but this is approximately 13. I'd say 1370 is close enough for that. So now we've talked about the solar radiation at the top of the atmosphere. We need to talk about what happens between there and when we collect it on the ground. Okay, so here we have it broken down pretty nicely, and there's that Planck curve again. The nice, smooth, theoretical spectral distribution of the radiation coming from the sun. And then overlaid, we've got that extraterrestrial spectrum. And then a little bit is lost due to absorption of ozone in a certain wavelength distribution there, which is shown as the green. Then a little bit of scattering by oxygen and nitrogen. That should be N2 as well. I'm sorry about that. Scattering by aerosols, which are so here we've got molecular effects, and the aerosols are larger particles in the atmosphere. And the way that the scattering occurs is dependent on the size, and we'll talk about that later. And then we've got some important transitions in water vapor where you see very spectrally dependent absorption, and there's some further absorption by different aerosols after that. Also, no, sorry, there was scattering by aerosols and absorption by aerosols, which are important for different reasons. So, and this is represented by this picture here where we have things like clouds, aerosols, scattering, aerosols absorbing, and then a fraction of the sunlight actually makes it to the surface to be collected and used. So even, I'd like to emphasize again, and it will come up again in the presentation, but the radiation that we can really use when we use CSP technology is that direct radiation. So any of this scattered, light scattered by clouds or by any smaller aerosols, it loses its directional information, and so we can't actually recreate that in any meaningful way with a concentrator. If it's scattered, it's more or less lost to our purposes. So that's why clouds are so devastating for CSP, because you don't get any direct radiation coming in. Although with PV you can still get about 20% generation even in cloudy conditions. And this is what I was talking about before. So when you've got scattering of oxygen, molecular oxygen or nitrogen. This is your Rayleigh scattering, and it's quite a different physical process to what happens when you have scattering of larger particles. And so the direction of the incident light is coming in from the left, and when you've got aerosols, you'll see that most of your radiation will continue to be scattered forward. But when you've got Rayleigh scattering, you've got a large component that's backscattered and scattered off to the side. So that's what happens when Rayleigh scattering is happening all through the atmosphere, because the atmosphere is just basically full of oxygen and nitrogen, and that's what the Rayleigh scattering effects correspond to. And that's the cause of why the sky is blue, actually. This directional dependence on scattering is also wavelength dependent, and it's heavily wavelength dependent. And so that's why we get more blue being directed down towards the surface of the Earth, and so we have what appears to be a blue sky. And of course that changes at sunset and it looks red because we're getting a different direction of scattering. And so I like to say that because I think it's a nice way of remembering this idea of Rayleigh scattering, because it's something that we see every day. So this is always going to happen, Rayleigh scattering, so it's something we need to just factor in. Mean scattering, not as much, because this is more about aerosol content in the atmosphere. There's ways of simplifying calculations of incident solar radiation where, as opposed to understanding the distribution of aerosols in the atmosphere or understanding the change in density from the surface to the edge of space, basically, edge of the atmosphere, we can simply talk about the air mass. And this is a sort of standardization where we have, when the sun's at the zenith, we have an air mass of 1. This is under specific conditions, mind you. And then this is more or less scales with the zenith angle, right? So as the cosine of the zenith angle. So as the zenith angle increases, and we've got this cosine of 60 degrees, giving a factor of 2, just simply because the sun has to travel through twice as much atmosphere to get to where we're to the Earth's surface. So just a nice little graphical representation here. We see the solar radiation being diminished at each point by these different causes. So we've got ozone, air molecules, which is Rayleigh scattering, the aerosol, which is more that Mie scattering, clouds, which can really destroy your operation, and water vapor as well. And then you finally get your direct normal irradiance at the ground, and we'll talk about what that means exactly in a second. And that's represented here in terms of a time variance. So it's one thing just to say, okay, how much loss do we have at a particular sun position under certain conditions, but we're also going to be interested in how that changes throughout the day. And of course, the sun is moving. We have also the possibility of cloud cover really coming in and affecting how much direct radiation we can collect at any given time. So understanding, in particular, how aerosols and clouds change throughout a day is really important for understanding some of the edge cases that you might run your power plant at, or just understanding how much variation you might expect to see, and how also an important topic in engineering for CSP power plants is understanding how to deal with these transients. And so in order to do that, answer those sort of engineering questions, we do need to understand what's actually happening in the atmosphere and the sort of variations we might expect. So just to make this diagram a bit clearer, the red here is actually what we collect at the ground, okay? And this is what we have at the top of the atmosphere, and everything in between is just showing you how much the radiation is attenuated by each of these effects. So the interim curves aren't that important. It's more what we have on the ground here. So yeah, that's not too important. I've mentioned this already, that we've got this direct light, and we've also got diffuse light. Diffuse light's not really interesting for us. It's just a bit of this is more text than I actually want to say here. So don't worry too much about reading all that. I just wanted to say that we've got global horizontal radiance, and this is the sum of the diffuse and the direct on the surface. And that's what you've got there. And this just means sometimes direct is called beam irradiance, okay? And really that's all there is to it. What we have here is a ratio, which is just another way of expressing this equation here. So this is all you really need to take away from this slide, this equation in the middle here, okay? Does anyone... so is that clear, the difference between global and direct? Okay, so I'll just quickly show how they relate to each other. So if you've got a surface here which is pointing directly at the sun, it's experiencing direct radiation. So it's perpendicular to the solar vector, we say, which is basically the vector pointing from the sun towards the Earth's surface. And when the sun makes an angle with the Earth's surface, then the radiation gets spread over a larger area. And the lower the sun is, then the more that radiation gets spread over. And the effective radiation incident on the horizontal surface, the flux density, is lower, according to a sort of cosine law. And here we see the relationship kind of, when I said cosine, I was talking about calculating the amount of radiation on the ground. But when you want to calculate the DNI from the radiation on the ground, no, forget that I said that. But here's just a relationship that shows the direct normal irradiance with respect to the direct horizontal irradiance, which is that direct component. When you consider how that angle causes it to be spread on the ground at a lower flux, that's what the direct horizontal component is. So I hope that's clear. The direct normal irradiance is always greater than the direct horizontal irradiance. Sorry, because the DNI can be zero when it's cloudy. And here we have the global horizontal irradiation. So this is when you've got the diffuse and the direct, you add them together, and that is basically how much solar radiation in total do you get on the ground. This is sort of more interesting for engineering of photovoltaic panels because, as I said before, the diffuse component's not interesting to us in CSP. And here we have some data from a given clear day overlaid with a clear sky model. And this shows our global horizontal irradiance, and then the direct normal irradiance here, which is much higher because you're pointing in this case, you imagine you're pointing your surface directly perpendicular to the sun, and then you see this diffuse radiation, and on a clear sky, it's not very high. It's less than 100 watts per meter squared, but it's caused by that Rayleigh scattering and that Mies scattering from the aerosols and from the composition of the atmosphere itself, the molecular composition. So just a quick word about the sort of spectra we might expect at the surface of the Earth, and the fact that there is a standard for that. So if you're doing any engineering that has any spectrally sensitive materials, perhaps you have a special paint that you've put on your solar receiver, and you know the spectral distribution of its absorption, then you can say, all right, well, I want to calculate how much sun I think that this paint is going to absorb. Well, I'll use this standard spectrum here, which is available for use. It's a sort of, and it's important to have standards, because then if everyone uses the same standard, and if it you know, so long as it reflects reality in a justifiable way, then if we all use the same standard, then we can make comparisons, or at least use the standard as a basis for some sort of comparison. So there we have the spectrum of the extraterrestrial radiation, and then overlaid we've got this air mass of 1.5 standard, which is, you know, it's I think for CSP, the AM 1.5 standard is going to be more interesting than the AM 1, because we're not usually building CSP plants in regions of the world where we have the sun directly overhead, because these are tropical regions. And so the air mass 1.5 corresponds more to latitudes in this sort of solar belt that they talk about, which is more towards 30, 40 degrees. Okay, and this is just the same picture, but with the visible spectrum overlaid, which I don't think is actually that relevant, but it's interesting. Yeah, and that's nothing new. We've talked about that. This is again showing the Planck spectrum, then the extraterrestrial, and then this AM 1.5, and there's just different transitions within there that are caused by oxygen, carbon dioxide, and H2O. It might be of interest just to point out that we've got the CO2 absorption bands in the infrared, which is exactly what causes the greenhouse effect. So the radiation leaving the Earth is shifted much towards the infrared, and so we get these huge absorption bands in CO2, but that's just an aside. So the motion of the sun from an observer at the surface. So we've got, of course, you know, we've got a few factors happening. I don't like that slide. We've got a few contributing factors, but the first thing I'd like to talk about is your latitude. So if you're on the Earth at the equator, then the incoming sunlight is coming at you directly, and it's spread over an effective area of this length in this diagram. When you compare that to sort of higher latitudes, let's say 45 or so, then you can see how 1 unit area of solar flux is distributed over a larger area on the surface. So this is again just demonstrating how the position of the sun in the sky affects how much direct radiation we can receive on any given patch of land, and in turn that is influenced by your latitude. So this is why it's particularly undesirable to build a CSP plant in Antarctica, right? Even though you might say, well, you know, they've got 6-month days. This is really reliable. You know, this could be great. A lot of our problems would disappear. We wouldn't have to shut down in the evening and so on. But of course, the reason it's so cold down there is they don't actually get a lot of solar radiation. So this is something to consider. And of course, then there's the apparent motion of the sun during the day, and depending on how you've got your module situated, depends on how much radiation you'll get at any given time. If you have a solar collector that's oriented 90 degrees, then you'll get a lot of sun in the morning. Of course, you'll have a higher air mass, so it won't be as effective, but then you'll get nothing at noon. And I mean, this is fairly obvious stuff, I think. Here we kind of sum up the way that the sun moves with respect to the Earth. So if you imagine you've got the ecliptic here, which is where basically if you're in the Earth's reference frame, we have the sun rotating around the Earth every day and of course, 1 extra time per year, because we have that whole motion around the sun as well as the Earth orbits. And we can see, if we imagine the sun coming around here, and at the winter solstice, it's shining from the bottom, and so you get less radiation in the northern hemisphere. We can see how the sun and the Earth system relates to one another. And the reason we've got this angle 23.5 degrees is because the Earth's axis is spinning on a tilt of 23.5 degrees with respect to the plane that the sun orbits around, the Earth orbits around the sun in. So these are all things that we need to consider when we're modeling how the sun is moving through the sky in order to model our solar resource. So we have, in order to do this, we define a time called solar time, which is not really a time. It depends. It's actually in units of. It's in units of. Well, let me see how it's defined here. So we've got the solar angle and the solar time. And the solar, but yeah, basically the solar time is the usually described in basis of solar time. Cosine the sun's path to the meridian. And it's the solar time. In solar time, 1 hour is 15 degrees of the sun moving in the sky, so that 24 of those adds up to 1 day. And the reason that that's interesting is because the day length throughout the year is not actually constant. And that's because of the elliptical orbit of the sun, but also because of the tilt of the axis. Right, so we've got this variation of the solar day length. And so when this becomes important, okay, in a practical way, when you're modeling the operation of a solar power plant, and you've got an equation that tells you where the sun in the sky is with respect to the solar angle, and then you've got DNI data, which is saying that at local time noon, at local time 1 p.m., the sun was this intense, you'd actually got a mismatch there because your local time is different from your solar time, and it changes throughout the year. And the way that we can characterize that comparison between the two is through this equation of time. And you can see how there's this, 2 harmonic effects that add up to one. The Earth's elliptical orbit, obviously it's got a period of 1 year, and the tilt of the Earth's axis has a period of 6 months. And then here's an equation. I believe that one's from Duffy and Beckman, Solar Processes book. And that characterizes the equation of time so that you can make sure that you're getting your DNI measurements at the correct time of corresponding to the sun location you're using. All right, so exactly, so this is the hour angle. 1 hour corresponds to an angle of 15 degrees. I was just introducing the concept of an hour angle, which is basically what I was saying before. Every hour in solar time corresponds to 15 degrees. Okay, so it's just another way of representing the time in terms of an angle. An important variable that will come up in any equation where you're characterizing the position of the sun is the solar declination. Now, the tilt of the Earth's axis is always at 23 degrees to the ecliptic, but it's the axis effective tilt from the point of view of the sun changes, because if you imagine this, so this axis is tilted at 23 degrees and it's going around the sun, but it's always tilting in the same direction. And at some point, if you're looking at this from the sun, it doesn't look tilted at all. You're looking, because the axis is tilted directly at you. That's when the declination is 0, okay? And then when you're 90 degrees from that and you're looking at the angle from the sun, you see that 23 degrees, and some of the Earth, no, in this case, some of the Earth will appear closer than other parts of the Earth, and in this case it will be, it won't be apparent at all. So what I'm trying to say there is that the effective tilt, basically this represents the seasonal effects here. And we've got the summer solstice depending on where in the world you are, in June, and we've got the winter solstice in December. And so the variation of the declination angle is given by this equation here, and you'll see that in any equation that requires you to calculate the position of the sun in the sky. Okay. Yep, so that's basically what I was saying, and at the equinoxes the declination angle is equal to 0. That's the point at which the day length is 12 hours, no matter where on Earth you are. The time that the sun is in the sky, I should say. And just another thing that needs to be considered is that the southern hemisphere, if you're in the southern hemisphere, then you need to be aware of how that affects your sun position equations. A lot of the coordinate systems are defined assuming that the sun is in the south, for example. This is something that, as an Australian, I've had to battle with in my research in the past when I was doing my PhD in the southern hemisphere. So it's something I've struggled with. Now we talk about the elevation of the sun. So we've basically got. Don't worry about reading all that. It's a simple definition. The elevation is basically just the angle between the ground and where the sun is. So how high the sun is in the sky in terms of an angle. And we've got the elevation at solar noon is actually dependent on the declination, okay, and also on your latitude. And this is of interest because often when we are choosing a design point to simulate our solar plant at, we might choose some sort of limiting case, like how does this power plant operate when the sun is in a position corresponding to solar noon on the summer solstice? Okay, and then we know the declination angle is 23.5 at the summer solstice. We know our latitude, and so we can say, okay, well, the altitude angle will be, let's say, 68 or so. And then that simplifies things quite a bit. Of course, there's the zenith angle, which is the complement to the altitude angle. It's just something to be aware of because often these sun position equations are expressed in terms of the zenith angle. So if you see that terminology, altitude angle, zenith angle, it's the same thing basically. One's the complement of the other. The azimuth angle, now because we're projecting onto a 2D surface, which is a sphere, basically we can characterize the position of the sun with two coordinates. So we've got the altitude angle and then the azimuth angle. So how high is the sun and in which direction is it pointing, basically. Here's a relation for calculating the azimuth angle. I do apologize that some of the terminology is a bit different. So we've got the HRA means hour angle here, which is that omega that was introduced beforehand. And this is just expressing the azimuth angle in terms of latitude, declination, time of day, and altitude angle, elevation angle. Okay. So this slide just reiterates the fact that depending on how your surface is pointing, if it's pointing directly at the sun, you're going to get more of that radiation, a higher flux than if it's laying directly on the ground. This is particularly interesting when you've got a heliostat field and you've got a tower in the middle. Those heliostats, they all have, based on the necessity to point the sun at the receiver, they have to angle themselves in a way that's not pointing directly at the sun. And so you get this cosine loss, that's what that's called. And that's why that becomes a very interesting, or I should say, important part of modelling a heliostat field. It's also interesting for troughs because they only track in one dimension, so you're always going to get some incident angle that's a function of the altitude angle of the sun. So this is called the cosine effect, and it's because you have this effective flux, which is a function of the angle between the solar vector and your surface multiplied by the direct normal irradiance. Okay. This summarizes the angles. So we've got this altitude angle, azimuth angle, and then we've got the surface tilt and the surface rotation. And you need to know those four angles in order to calculate exactly how to calculate basically the two vectors, which is the solar vector and the normal vector of the surface, which will give you the cosine calculation. So that's basically summarizing a lot of stuff we've talked about. It's reiterating the fact that it matters what your latitude is, and also the different values for the radiation at the atmosphere and then on the surface. 1,000 watts per meter squared is often used as a kind of limiting case or design point for solar power plants. If we imagine that we are getting 1,000 watts per meter squared, then we're being on the safe side, because you're not going to get much more than that. You can get 1,100 in some places under some conditions, but 1,000 watts per meter squared is usually a good design point to use for those kind of design calculations. We've got half an hour left. So that's a lot about the apparent position of the sun and the sort of causes of attenuation of direct normal irradiance through the atmosphere. But here we're going to talk about the annual solar resource. And so this is basically a metric. It's a sort of a coarse measurement or indication of how successful you might expect a solar power plant to be if you built it in a given location. So basically, how much solar radiation do we get over the whole year? So you're integrating the direct normal irradiance over an entire year to get that value. And as we can see here, if we assume a peak intensity of 960 watts per meter squared, then based on your latitude, so comparing Iceland to southern Spain, then you get around 12% over the year of what you might expect if you were getting that constantly. And this is a way of describing the intermittency of your solar radiation. In southern Spain, it's much higher, obviously because you're not getting so much cosine losses there. So it's a measure of the intermittency of the solar energy source. And this doesn't vary too much from year to year. So if you have a good understanding, say if you have a number of years over which you've characterize your solar energy source, then you can get a fair idea of how well a power plant might perform at that location. Here we have, we've seen these maps already in Luca's introductory talk, so I'll just go over them quickly. Here's the global horizontal irradiance around the world. Here's it compared to the direct normal irradiance. As Luca mentioned, we've got some pretty nice looking spots in the USA and Chile and in Australia. And just zooming in on Africa and Europe, we can see a comparison between the two. And around the equator, there we see that these tropical areas have a lot of clouds associated with them, which diminishes that direct normal irradiance a lot in comparison to the global horizontal irradiance. So you can see why a lot of those power plants have gone up in Spain. It really is a lot better than mainland Europe, than the rest of mainland Europe, and so the south of France is not bad either. So how do we measure the solar resource? Well, this is also something interesting you might come across if you're doing research in CSP and you want to take your own measurements. If you want to do experiments, you might have a solar Fresnel collector like they have out the side here, or a parabolic trough experimental setup like they have at ENEA, or the dishes they have there in fact as well. Then you might want to take your own measurements in order to characterize the performance of your solar collector with respect to the amount of incident radiation. So there's different ways of doing that. We have what's called pyrheliometers. Here there's differentiated between two types, but basically those two types are both used to measure the direct normal irradiance by having a narrow field of view. And then we have pyranometers, which measure all radiation incident on the flat receiver. So basically that's getting that global horizontal irradiance. And if you have the global irradiance and the direct irradiance, then you can make a guess at a good estimate of the diffuse irradiance as well, of course, subject to the measurement errors. So here's a picture of the pyranometer, which is measuring the direct normal irradiance, and we can see it's quite long, so it's, this is in order to limit the field of view. There's a bar here for mounting it onto a tracker because this has to track the sun. If you're not looking at the sun, you can't measure the direct normal irradiance. So here we see a 2-axis tracker onto which the pyranometer is installed. And measurement uncertainty here is cited at about 1%. In addition, we have the pyranometer for measuring the horizontal irradiance, and the uncertainty here is a little bit higher, between 2% and 5%. And here we see it installed onto onto a stationary T-bar here, which has also an instrument here called a shadow band shading ring, for blocking out the direct irradiance. So that's what you would use if you wanted to measure the diffuse irradiance. And that has quite a bit higher uncertainty, I suspect, because the diffuse irradiance is generally a lot lower than the global horizontal irradiance. As you might imagine, if you block out the sun, you get a lot less of a signal. So we can also derive irradiation data from satellites. So this is quite an interesting piece of research, which area of research, I should say. And here we have an example of the Meteosat satellite in geostationary orbit. So this satellite is looking at one specific part of the Earth, and it doesn't move. And it scans the Earth line by line every half hour, and it's just sitting there rotating. And it's scanning the Earth kind of like a television, an old cathode ray television, where you're doing it line by line, and then you're resetting and then going again. I mean, if you can imagine this little thing just spinning there in geostationary orbit and just moving its sensor down a little bit each time, and then it gathers. It's a passive device, so it's basically just receiving the light that's scattered from the Earth, and using this sort of device, we can backwards calculate how much radiation we expect might be incident at the surface by characterizing cloud cover and other using other models to predict how much aerosol effects and Rayleigh and me scattering we might expect